The next thing we're going to look at is a power series that defines a function. We say that a power series defines a function, that is, that a function f of x can be written as the sum as n equals 0 to infinity of Cn x minus a to the n, whose domain is the interval of convergence of the series. So the domain of this function f of x will be all values of the real variable x, such that this sum converges to a real number. If the radius r is greater than 0, or if r is equal to positive infinity, meaning if it converges for all real numbers, then f is continuous, differentiable, and integrable on the intervals a minus r to a plus r, or on the entire real numbers. Moreover, f prime and the antiderivative of f of x dx can be found by either term-by-term differentiation or term-by-term integration within the series. Convergence at an endpoint may be either lost by differentiation or gained through integration. So the radius of convergence that we have, in particular the interval of convergence, whether or not the original series converges or diverges at the endpoints, may very well be different for its derivative or its antiderivative. We might have a series that perhaps converged originally. We take its derivative, and then we might find out that at that previous endpoint of convergence, for the derivative, it might diverge at that endpoint. So, as always, we need to take care when dealing with the endpoints to see whether or not we have convergence there. So, for example, let's suppose we have the sum y equals c to the n x to the n. If we wanted to write out the individual terms of the series, when n is equal to 1, actually there's a typo in the notes. They actually meant for this index to be 0, because look, they made a mistake here. When n equals to 0, this would be c0, and then when n is equal to 1, we get the c1 x to the first, which would be this term here. When n is equal to 2, we get c2 x squared, which would be this term here. And then we know how to differentiate something like this. The derivative of c0 would be 0. The derivative of c1x would be c1. The derivative of c2x squared would be 2c2x. And in general, if we look at just differentiating the nth term on this thing, you bring the power down and then reduce the power by 1 like we're used to. So the first two derivatives of this thing would be y prime would be equal to the sum from n equals 0 to infinity of n times x to the n minus 1. Of course, we would need the c term there. And then y double prime would be the sum from n equals 0 to infinity. Just differentiate it again. You bring the power down again. This would be n minus 1. Reduce the power by 1. We would get x to the n minus 2. Okay. One of the things that we would notice is that these first few terms, so when you differentiate, for example, the first derivative, this constant would be 0. And so we wouldn't need to include that 0 term. So we actually would lose one term from the sum. So when you differentiate, those constants kind of drop out. And so the first term would be 0. So the sum would then start at 1. When we take the second derivative, not only the constant, but that first order linear term would be 0 as well when you take the second derivative. So we're essentially losing the first two terms because they're 0. So notice that the derivative would start at n equals to 2. And this is true in general. If you take the nth derivative of our power series, if it started originally from n equals 0 to infinity, the nth derivative would start from, maybe I shouldn't say nth because we have an n here, but let's say kth derivative. The kth derivative of y would start from n equals to k to infinity of the derivative of your inner expression. A couple of fundamental properties that we have for power series is what's called the identity property. Let's suppose that our power series is equal to 0 for r greater than 0 for all numbers x in some open interval. Then the only way that this can happen is if the coefficients c sub n are equal to 0 for all n. So if this function is equal to 0 on some open interval, for all numbers x in some open interval, then all of the coefficients must have been equal to 0. The next thing we come to is an extremely important definition in higher mathematics, which is the concept of being analytic at a point. So please, in your notes, star this, make note of this. But the property of being analytic at a point is extremely important. We say that a function f is said to be analytic at a point A if it can be represented by a power series in x minus a with either a positive or an infinite radius of convergence. Okay. In other words, it's not just enough. R cannot be 0 in this case, meaning that the power series cannot converge at just the center A. We need it to converge in some open interval containing A, which means that the radius of convergence has to either be a positive real number or it could even perhaps converge for all real numbers. In calculus, it is seen that infinitely differentiable functions, ones like e to the x, sine x, cosine x, e to the x, ln of 1 plus x, etc., we know that those things can be represented by Taylor series. The Taylor series, if you remember the formula for the Taylor series, it's the sum from n equals 0 to infinity. It's the nth derivative of the function evaluated at the center divided by n factorial times times x minus a raised to the nth power. And we can kind of go ahead and write out the first few terms of this Taylor series. When n is equal to 0, we would get the 0 power for this, so that's going to be 1. The 0th derivative would just be, the function evaluated at the point A, and 0 factorial is 1, so this is going to be equal to f of a. When n is equal to 1, we get the first derivative evaluated at a over 1 factorial times x minus a to the first. And here's another typo in the book. For the second derivative, we should get 2 factorial on top of, or below f double prime of a times x minus a squared, and it just kind of keeps on repeating. A very special instance of the Taylor series is what we call the Maclaurin series, which is simply when your Taylor series is centered at a equals to 0. So if a equals to 0, then we get the Maclaurin series, which would have the following form. It's the sum from n equals 0 to infinity, the nth derivative evaluated at 0 divided by n factorial times, again, if it's 0 for a, then this simply reduces to x to the n. And likewise, if we wanted to, we could write out the first few terms of this series as well. And again, typo in the text, this should be over a 2 factorial. It's a common exercise, especially in Calculus 2, to try to compute the Maclaurin series for a couple common functions. For example, the Maclaurin series for e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, which we can write in closed form, summation notation, as the sum from n equals 0 to infinity of 1 divided by n factorial x to the n power. The cosine, which you might recall from trigonometry, which is an even function, correspondingly has only even terms in its Maclaurin expansion. The cosine of x is equal to 1 minus x squared divided by 2 factorial plus x to the 4th divided by 4 factorial minus ... We have this alternating sum. Again, to write it in closed form, notice that what we have is an alternating sign, so that's going to be provided by the negative 1 to the nth power. And then what we have is simply the even coefficients in the numerator for our x, so it's going to be x to the 2n, divided by the factorial of that power, so it's going to be divided by 2n factorial. And then we have a bunch of other ones that are listed. I will post in D2L this kind of list of these common Maclaurin series, but it's extremely important to kind of memorize some of them, or certainly at least be able to be handy to look them up when needed. Okay. We can also use these to kind of generalize to find Maclaurin series for other functions. For example, we don't have to reinvent the wheel every time. Let's suppose we wanted to find a Maclaurin series for e to the x squared. So let's kind of go ahead and do that. Well, one of the things that we know is if I write out the series for e to the x. So again, e to the x, this was equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc. This was the sum from n equal to 0 to infinity of 1 divided by n factorial x to the n. And here, in this Maclaurin series for our basic function e to the x, our input or our variable is x. if we simply do the substitution, if we replace x with x squared, then this would produce the following series for e to the x squared. So it's going to be 1 plus, and I'm going to overemphasize it with parentheses, but it's now going to be 1 plus x squared plus, let's write out the form of this thing, input squared divided by 2 factorial plus input cubed divided by 3 factorial plus dot 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 dot. Everywhere we see an x, we're simply substituting it with x squared, and this would produce 1 plus x squared plus x to the 4th over 2 factorial plus x to the 6th over 3 factorial dot 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 dot, which we can also write in closed form by doing the same thing. Let's make a substitution into our summation notation here. Wherever we see an x, we can replace it with x squared, and therefore we find that the closed form summation notation for e to the x squared is going to be 1 divided by n factorial x to the 2n. So by just simply knowing the Maclaurin series for some of the basic functions, we can utilize them either via direct substitution, or sometimes we can get clever and integrate or differentiate in order to find the Maclaurin series of some new functions. Okay. So again, that list will provide us with a lot more information than what it might look like on the surface. We could do kind of like the same thing too. If we wanted to find, let's say, a Taylor series expression for the ln of x, but let's suppose we want it to be centered at a minus, let's say at a equals to 1. If we're going to be centering it at a equals to 1, then essentially what we would like to do is we would like to replace kind of like the x by the x minus 1. So let's kind of come back here. Now the Maclaurin series that's given in the textbook is not just for the ln of x, it's actually for the ln of 1 plus x. So for this variable that's right here, we would like for this to be an x minus 1. And then what you see is that in that series that's written in the textbook, everywhere we see an x in the power series expansion for the ln of x, we get x minus 1 minus x minus 1 squared over 2 plus x minus 1 3 to the third power over 3, which is equal to negative 1 to the n plus 1 divided by n times x minus 1 to the nth power. One of the things we want to comment on before we look at the next example is the arithmetic of power series. Power series can be combined through the operations of addition, multiplication, and also division. The procedures for power series are similar to the way in which two polynomials are added, multiplied, and divided. That is, we add the coefficients of like powers of x, and we use the distributive laws to collect like terms and to perform long division. Let's take a look at an example of one of these. In example 2, we're asked to find a power series representation for e to the x, the sine of x. So one of the things we can begin by doing is we actually know a power series for e to the x. So e to the x times the sine of x, and I'm just going to write out the first few terms here. E to the x we know is simply going to be equal to 1 plus x squared over 2 factorial, which is 2, plus x cubed over 3 factorial, which is 6, plus x to the 4th over 4 factorial, which is 24. And I'll do one more term, plus x to the 5th divided by 5 factorial, which is 120. And then this kind of keeps going on and on forever. Then we're going to write out the first few terms for the sine of x. We know that the sine of x is x minus x cubed over 3 factorial, which is 6, then plus x to the 5th divided by 5 factorial, which we know is going to be 120. This is an alternating sum, so the next term would be negative, and that pattern would continue forever. Okay, so we're going to do this kind of infinite multiplication, and if you remember back to kind of like your experience with multiplying binomials and trinomials from algebra, we would have to use a super generalized distribution property where, for example, you would start off by taking the 1 and multiplying it to every single term in the second series, which would result in infinite multiplication. Assuming you could do that infinite multiplication, we would then move over to the x and likewise distribute it to every term in the second parenthesis. Well, because this is an infinite product, we're not going to be able to multiply every single one of those terms out. It's just impossible. But we can say that maybe we want to write the answer, at least maybe the first few terms of the solution. And let's suppose that we want to get up to the 5th power of x. So let's write out all of the terms up to the x to the 5th from this series. The way we can do that is, let's start with the first term here, the 1. I'm going to multiply the 1 by every term in the second parenthesis until we stop and get terms that would exceed x to the 5th. So 1 times x, that would give us x. We would then do the 1 times x cubed divided by 6, and then the 1 times x to the 5th divided by 120. And then we could stop there because the next term in this series would be a negative x to the 7th term, which is beyond the order that we're going here. Now that I'm done with the 1, we're going to repeat the same thing. Let's begin by multiplying the x term into the second parenthesis, and again stopping once we go beyond the x to the 5th power. X times x would give us a positive x squared. X times a negative x cubed divided by 6 would give us a negative x to the 4th divided by 6. And now if I do x times this next term, that would result in x to the 6th, which is beyond what we're looking for. So I'm going to stop with that part. I'm going to now move over to my next one. Let's take x cubed over 6 and start to distribute it. X cubed over 6 times x would provide us with an x to the 4th over 6. The next term would be x cubed times an x cubed, which is x to the 6th, so that's already too much. So we're done with that term. Let's come over here. If I take x to the 4th over 24 times x, that will give us an x to the 5th over 24. And then x to the 4th times the next x cubed term would be x to the 7th. That's beyond what we want. So I'm done with this term. And now we realize that very quickly, if I tried to distribute any of the terms from x to the 5th or beyond in the first parenthesis, that they're going to multiply originally to that x term, and those will already provide us with terms that are going to be beyond x to the 5th. So at least up to the 5th power, this would be the terms for the power series e to the x, the sine of x. Let's try and combine what we can, writing them in standard form from lowest powers to highest powers. So we have an x term, which is right here. We then have an x squared term, which is going to be right here. We have a x to the cubed term. This is x cubed over 6. Now our x to the 4th terms cancel. We have a negative x to the 4th over 6 and a positive x to the 4th over 6. So those cancel. And then we have some like coefficients we can combine here. We have a 1 over 120 plus a 1 over 24 x to the 5th. And so this is going to end up being equal to, we have x plus x squared. And I feel like I'm missing an x to the cube term. Let's see if we can squeeze it in here. I think we did miss one. So 1, 2, 3 is good for that. 1, 2 is good for that. Somehow I totally missed the boat on the x squared over 2 times x. We should actually have an x cubed. Sorry, this multiplication here, I don't recall writing that out. Give me 1 second here. Okay, so looking back through it, actually I didn't distribute anything with the x squared over 2. My apologies. X squared over 2, when we multiply that by x, that would have given us x cubed over 2, and then also x squared over 2 times a negative x cubed over 6, that would have given us a negative x to the 5th over 12. So let's kind of go back here and kind of work those terms in. The first little bit doesn't change. We have an x here. This is an x squared. Now we do have two x cubed terms. We have this one with a coefficient of negative 1/6, and this one with a coefficient of positive 1/2 x cubed. So that takes care of those two. As we said a moment ago, all of our x to the 4th terms cancel, so they're gone. And now we actually have three x to the 5th power terms. This one has a coefficient of positive 1 over 120. This one has a coefficient of 1 over 24. And this one will have a coefficient of negative 1 over 12 x to the 5th. We can now go ahead and combine those like coefficients. We have x plus x squared. Just off the top of my head, I know that this is going to be a positive 1/3 x cubed. Now I'll leave the arithmetic to you. I'm just going to punch it into my calculator. If you do 120 plus 1 divided by 24 minus 1/12, and then of course leave it as a fraction, get common denominators, that's going to end up being a negative 1 over 30 x to the 5th. And then of course, this is just but the first few terms of the power series of e to the x sine x. And so some people might look at this infinite sum and be like, well, there's no way to ever write out this infinite sum because we can't do an infinite multiplication conceivably. Yet at the same time that we've just demonstrated that if you tell me what power of x you want me to write up to, we can certainly demonstrate and write all of those powers of x. Therefore, especially if you have things like a computer, you could, loop this and continue to do that distribution and write out the power series of e to the sine x to any finite number of places that you wish by simply just going through a ton of multiplications.